again. My name is Micheal Bretti. I'm the founder of Applied Ion Systems. Today I'll be just sharing a bunch of the research and developments that I do and kind of my approach in propulsion, particularly how Applied Ion Systems takes these normally complex types of propulsion technologies and makes them more accessible for many types of nanosat and picosat groups. So I have a bit of a presentation that walks through everything, which I'll share on the screen, and then afterwards I'll open up the floor to answering any questions anyone has about anything, either technical about electric propulsion or from the business side, or really anything you want to ask about this effort. So let's see if I can get this presentation up. All right. Can you see the presentation?
Yep.
Okay. So a little bit of a background. I'm the founder of Applied Ion Systems, and currently, as far as I'm aware, this is really the only independent maker-based at-home R&D company for advanced plasma and ion thrusters, really with the goal of making ultra-low cost, easy to manufacture, and open source thrusters for the nanosat community. As well as providing resources for hobbyists, educational enthusiasts, and satellite communities. So a little bit of my approach, which hopefully you'll be able to see more of throughout this presentation. The core aspects of everything I do is really centered around open development and transparency. So actually, all the thrusters that you see here, you can find the design files and everything for them. So you can actually go and see how everything is designed and built. I also document everything extensively and post on things like Twitter and Instagram and show every aspect of it, from the initial sketches all the way through testing and end of life for these systems. And through this, I provide lots of resources, knowledge, and firsthand experience in EP that a lot of times you really won't see through an academic setting. When people present this stuff, they always show the final results, but very rarely do you see the behind the scenes of how these types of technologies are developed. Everything is focused on very low cost developments. Right now, I don't actually have any official funding myself, besides a few $100s a month through Patreon and some out of pocket. So I have to keep everything super low budget. As well as simplifying my infrastructure and testing, using a very compact, low cost and simplified vacuum chamber, as well as relying on very simplified manufacturing. All the thrusters you see here are built with very readily accessible technologies, simplified CNC geometries, 3D printing is heavily used, laser cutting, so everything that is pretty readily available, and because I can't have access to more advanced manufacturing technologies. In addition to this, AIS also heavily engages with the community, so working very closely with nanosat and picosat groups and really developing and catering these systems towards their needs. There's a lot of groups out there who would like to use propulsion, but current systems on the market are just too costly, and there really isn't much incentive to bring it down for these groups. So I work a lot in this area to try to make it more accessible for everyone. So just a very brief background. Electric propulsion itself is an incredibly diverse field. There's just so many technologies crammed into this, and that's one thing that really makes it as exciting, is you can never really get bored of the field because there's so many areas you can branch into. There's a few major categories of electric propulsion. So there's electrothermal, like resistojets, where you just have electrical energy heating up a gas. You have plasma, so a whole bunch of different types of plasma thruster systems. So everything from DC, ArcJet and MPD, to RF types of plasma, spanning from low frequencies to microwave frequencies. And then a variety of pulse plasma thrusters, like Teflon fueled vacuum arc, which uses metal fuel, pulsed inductive thrusters, which use pulse gas supplies. And then finally, you get into the category of ion thrusters, where you have, again, a whole dizzying array of technologies. Everything from gridded ion, which has several categories in itself, old style contact ionization, like used with cesium thrusters back in the 60s and 70s, And then more recent and more modern systems that use hollow cathode or RF type cathode type ionization mechanisms. You have, of course, the classic Hall effect thruster, and even in that category, you have tons of different variations. You have stationary layer, you have anode layer, end hall, cylindrical, and then other variations in between. And then some of the newer types of ion thrusters in the field, electrospray, with FEEP, or field effect electric propulsion, which uses liquid metal fuel, and then ILIS, which is something that I work on myself, ionic liquid ion source, which uses room temperature molten salts. So electric propulsion covers a huge range of technologies, a huge range of applications for delivering electricity into the fuel to ionize it, and then a whole bunch of different fuels. Everything from solids, you have plastics, you have metals, you have liquids like water, ionic fuels, liquid metals, and then you have the gases, xenon, argon, some very unique ones as well that I'll be covering later in the presentation. So many, many, many options for these types of technologies. Now, there's a few key considerations for electric propulsion. The biggest and most fundamental one is power. Power ultimately defines the performance that you can achieve and really defines what technology class you can select for a particular scale and mission. Different technologies scale better than others, and at some points, some technologies make more sense. So by knowing the power budget that you have available for electric propulsion, that can already tell you a tremendous amount of what performance you can expect, as well as what technologies would be best in the range for you to apply to a particular
Michael,
problem.
I'm so sorry to interrupt, but I think
Yes.
your PPT is freezed. Are you still on the first slide?
No, I'm further along.
Yeah, I think it's freezed for us. Is it for me or
Oh yeah,
it for
it is frozen.
Please run.
Oh, now it's moving.
Yep.
Do you see it now?
Yeah.
Yeah, are you on the third slide?
Yeah. Can you see this now?
Yeah.
With all the pictures?
No, it's on the slide before that.
So the AIS approach slide?
Yeah.
Let's see. Can you see it changing at all?
It just changed to the fourth slide.
Huh, that's unusual. It seems like when I'm in presentation mode, it's freezing for some reason on your end.
Do you want to try stopping the screen share and trying again?
Yeah.
That could work.
Let's see. Let me see if I can get this up.
Oh, also, Mr. Michael, I had a question for you.
Yes.
So what was it that drew you towards propulsion? To the point where you actually made your own business with it and actually are having a lot of, a lot of breakthrough, you're doing a lot of good things. So what drew you towards it?
So for me, electric propulsion has really been, combines a lot of areas of interest of mine. I've always been interested in plasma systems, in ion beam and electron beam particle physics systems, high vacuum physics, and propulsion in general. And electric propulsion allowed me to combine everything that I really love to do in one field, while also being so diverse that it allows me to explore many, many different types of technologies. So, I can, if I want to, I can explore a whole bunch of different types of plasma technologies. If I want, I can explore a whole bunch of different ion technologies and electron technologies for neutralizers and stuff. So it's a very diverse field that allows me to do a lot. And there's also, I found, a big need within the community, especially going down into the pocket cube class size satellites, where there really isn't, there's almost no commercial systems out there for these types of satellites. You're starting to see some stuff emerge at this scale, but it's still a very, very new field. So there's actually a lot that can still be done. And one of the biggest challenges in electric propulsion is actually scaling down. So a lot of stuff that can be done, which makes it pretty exciting.
All right.
So can you see this screen now?
Yeah.
Can you see it change?
Yeah. Yeah.
Okay. So yeah, I must have been messed up sharing. So can you see the screen now with all the propulsion technologies on it?
Yep.
Okay. So I already kind of gave you the spiel about the different types of technologies. So I apologize that little bit messed up. But again, you can see there's a huge diversity in technology for electric propulsion, which again is one of the reasons that drew me to it. Is just because there's so much you can explore across many different types of fields. So again, going back to the key considerations, I discussed power a little bit earlier. Another key consideration for propulsion that's a limiting factor is size. So not only do you have power constraints that define performance and technology class, but also size determines many aspects as well. And in particular, in electric propulsion, one of the biggest challenges facing the field right now is scaling technology smaller. It is a challenge to balance performance with scaling. At the larger size and the higher power, if you're talking about kilowatt class thrusters, which really is where the field kind of started out to begin with, scaling in terms of performance is much easier. But going down into several tens of watts or less, there's a lot of challenges in that. And then going in with the performance, there's always trade-offs between power, thrust, ISP, and size. And certain technologies lend themselves better to different applications. So there's never one perfect solution that fits everything. I never subscribe to the idea that one propulsion system is superior to others. Even the debate between chemical and electrical, they both have their own place and they can both be used to complement each other. So major challenges facing the electric propulsion field currently, again, I covered it here, scaling, and especially for the increasing demand in smaller platforms. You're seeing a lot of companies now releasing CubeSats and looking at CubeSat technologies for flocks and swarms, and things are getting much more powerful. Even in the pocket cube community, where pocket cubes are 1/8 the size standard of a CubeSat at 5 by 5 by 5 centimeters, you're seeing some very rapid advances in power capabilities and in other payloads, which are opening the needs now for smaller and smaller propulsion. And one major thing that I think is kind of overlooked in the field in general is that smaller thrusters themselves do not necessarily mean smaller thruster systems. Actually building a thruster head very small itself is rather easy. That's actually one of the easier parts of scaling. The really big challenge that I feel that needs to be addressed still is everything that goes to supporting that thruster head. So the electronics, the fuel, and all the auxiliary, that's where the challenge in scaling really lies. Another key challenge is cost. Propulsion systems currently are besides specialized scientific payloads, are really the most expensive subsystem on a satellite. You're talking about tens of thousands of dollars for small pulse plasma thrusters or micro ion thrusters like Electrospray you see on the markets. And then larger and higher power systems like Hall effect and gridded ion and RF plasma, hundreds of thousands of dollars for these types of systems. So it's very cost prohibitive, especially at the smaller scale where you have a lot of groups where the cost of a propulsion unit literally costs as much as the launch or more than the satellite itself. And then finally, the convention of the field. Normally it takes electric propulsion is developed from often a PhD spin-off or program. That's 10 or 15 years development prior before something spins off and gets to initial prototype for a space company. And requires multi-million-dollar funding and government contracts. Very complex manufacturing processes a lot of times, especially with things like Hall thrusters, where you have to have custom ceramics for the discharge channel. And there really hasn't been much financial incentive to bring these systems down to a more accessible level, especially for nanosats. Very few have actually flown electropropulsion compared to larger satellites due to cost and technical constraints. And finally, one thing that I like to mention before I get into actually showing some of these systems is that whenever you see electropropulsion kind of in media or when it's talked about in general, it's always hyped up as some super sci-fi magic. It's always some out-of-reach, insane NASA tech that's state-of-the-art, cutting edge, and it's not really. Electric propulsion is actually a very old and well-established field. I mean, you find the basics of all these systems going back to the 50s and 60s. And all of electric propulsion actually shares the same basic principles with many technologies already explored and well-established in many other fields. So for example, gridded ion thrusters, they're literally just broad beam ion guns. And you can find these in particle physics, you can find these in physical vapor deposition processes, semiconductor manufacturing. Same with Hall effect thrusters. These are very common in industrial processing as gridless end Hall sources or anode layer sources. RF plasma thrusters, these share the same basic principles as inductively coupled plasma torches. The electrospray thrusters like FEET, which uses liquid metal ions, this is a common technology used with focused ion beam milling. And then electrospray with Illis and colloidal, you find these technologies in printing and in chemistry analytics, and then things like ArcJet and MHD. These share the same exact principles as plasma torches. So by knowing this, you can really broaden your knowledge by looking at the general principles across multiple fields and gain new insights by looking at how there's all of this crossover between many other technologies. And in fact, the inspiration for the Hall thruster that I'm developing, which I'll get to at the end, I drew inspiration not from electric propulsion type systems, but from industrial processing systems for the thruster head, and then looking into particle physics, some kind of experimental neutralizer type setups that aren't used in electric propulsion. So when I approach electric propulsion, I don't necessarily approach it from the standpoint of developing, a Hall thruster or an ion thruster, but more broadly as a plasma source or an ion source that's catered towards kind of pushing a satellite. So it keeps things more open and flexible for development. So getting into some of the thrusters that I built, this was the first fully completed system, the oldest one that I've worked on and kind of the most successful to date. This is the GPPT-3. So this is a micro pulse plasma thruster. So everything you see here is the full thruster itself. You have the thruster head, you have the high voltage and low voltage electronics. All the fuel is integrated because it is just Teflon fuel. So very, very small, very compact plasma thruster. So you can see kind of the size of it, 40 by 30 by 24 millimeters. It requires 5 volts in at only 500 milliwatts, so half a watt of power total for the thruster. Thrust is very low. Again, like I mentioned, power defines performance. So at lower power levels, it's challenging to bring performance up. But at something like this is really meant to allowing anyone to explore the fundamentals of propulsion and look at basic control and use of such systems on their satellites. So a very compact and simple system to actually build and use. Here you can kind of see the actual thruster head itself. So the thruster itself is extremely easy, literally just a couple of copper plates and plastic plates bolted together. That's it, that's all of it. And you can really drive this with any high voltage electronics. I made the electronics very small and specifically designed for pocket cubes. But this can be adapted to really any type of general pulse circuit to drive. So here is actually a video of it firing. It fires at a lower repetition rate because it's limited by power, so the power limits how fast it can fire. So you can see, I don't know if you can see the purple flashes once in a while. So it's firing at about once every 3 seconds. So this was actually one of the first qualification tests of the thruster when I was developing it about a couple of years ago, right when I started. So since then, I've had a few collaborations with this particular thruster. The first one, this was actually literally within the first year of me starting my whole Applied Ion Systems effort, even before I actually became an official company. The two of these units were provided to the AMSAT Spain team to be integrated on their Genesis NNL pocket cubes. So they're 1.5 P. So 50 millimeters by 50 millimeters by 7.5 millimeters, or 5 centimeters by 5 centimeters by 7.5 centimeters satellite. So you can see the thruster kind of integrated into the satellite at various stages. It's passed all the thermal and vibration, and it's literally on the Firefly Alpha launch. It's been delayed over a year now, but hopefully it actually should be going up potentially this June. So crossing our fingers to see how this launch goes. Then next, this was a more recent collaboration with the Care Weather Technologies Hatchling Veery. So this is a 1U CubeSat for weather monitoring. So you can actually see the thruster sticking out the back of the actual CubeSat itself. And as of March, this thruster is actually in orbit at 550 kilometers. So this is actually, as far as I'm aware, the first fully open source, literally home-built thruster in orbit now. They haven't fired the thrusters yet because they're going through a lot of other critical mission stuff first, so the thruster testing will come later. However, this is also the first AIS thruster to make it into orbit, and the CubeSat has phoned in and they're collecting data, and really excited to see how this particular mission goes. So like I mentioned, because the thruster head itself is so simple, it allows you to really play around with a whole bunch of different driving technologies. So here you can see a couple of experimental boards. On the left, you have, I'm using 2 pulse transformers and a slightly larger capacitor. And on the right side, I'm using a much bigger pulse transformer coming out the back, and then a much larger pulse capacitor. So kind of looking ways to further push performance with this particular thruster. So here's another video of it firing. As a warning, the flashing rate on this is much faster, so there could be I would say this is kind of a seizure warning. So anyone who has any problems with that, please look away before I start this, because this will flash quite fast. So I'll be starting this now. So you can see this thruster is actually firing at a much faster repetition rate. So a little bit higher power actually goes a long way in terms of performance. This is flashing at about 3 hertz, so 10 times the repetition rate of the original module, which ultimately means 10 times the thrust. So this is looking at pushing the micropulse plasma thruster to higher repetition rates, which generally they're limited to only about a few hertz max. So moving on, we have an even more advanced thruster. This one is particularly exciting. This is an ionic liquid electrospray thruster. So as I mentioned prior, ionic liquid ion sources actually uses room temperature molten salt fuel. So the basis of this thruster is that capillary action wicks liquid from a reservoir to the emitters, which is drawn out by high field strengths, and then you accelerate the ions. And what's unique about this type of thruster is that because of the fuel used, you can actually extract both positive and negative ions. So that means you could have self-neutralizing beams, which makes it a very, very efficient technology. And because the emitters can be manufactured extremely small, this lends itself well to very, very small scaling, which is perfect for CubeSats and Pocket Cube class systems. So you can again see the thruster on the left. This is everything. This is the high voltage. This is the thruster, the fuel storage, and all the switching used. And then on the right, you can actually see a bit of the beam firing out into a Faraday Cup to collect current. So this is also a very compact system, 45 by 45 by 16 millimeters, very low mass. The fuel is EMI BF4, which is a type of ionic liquid. It's a very, very common liquid, actually explored a lot in chemistry and biology. So it's very well studied, and it's been recently applied to electrospray in the past few decades, because it has a lot of promising potential in these things. And there's already several companies out there developing these systems commercially at the larger scale. So normally these types of systems utilize laser ablation micro-machined emitters, or MEMS emitters, which are obviously way too expensive and complex for me to do myself. However, there have been recent developments in CNC machined glass. So instead of microscopic emitters, you have larger structures machined out of common glass. And this is something that I've been exploring myself. So far, I've gotten a thrust of about 3 micronewtons at very high ISP because of the high accelerating voltages, over 5,000 volts on the system, at very, very low power levels, less than 0.1 watt. So very compact, very efficient, high thrust to power ratio, and very high ISP. So you can see here, kind of, again, going back to the simplified manufacturing approach. On the left, you have the glass emitter. So this is actually just standard chemistry frick glass. You can purchase this really from any chemistry supplier. It's a standard glass disc used for filtering, where the spike is machined into. And then on the right, you can actually see the 3D printing housing, which holds the reservoir and the emitter. So I actually use 3D printing very heavily in all my thruster systems, not only because it allows me very cheap and rapid prototyping, but for a lot of the systems that I'm doing, I can actually get away with 3D printing, because, like, for this type of thruster, heat isn't really an issue. So I don't have to worry about kind of issues that you might expect with something like a Hall thruster. But even that, you'll actually see there are ways to get around it. So this is a video of the Electrospray thruster actually firing. So you can see the ion beam coming out, and then right there is actually a polarity change. So like I mentioned, depending on the polarity applied, you can extract both positive and negative ions from the thruster itself. So by switching back and forth and alternating between positive and negative, you can actually achieve charge neutralization of the beam and the spacecraft. So getting one step further into some very advanced experimental fuels, currently Applied Ion Systems is actually leading developments into a very, very unique fuel. This is called adamantane, which, as far as I'm aware, no other company on the planet in electropropulsion is actually doing. Now, adamantane is very unique because it is a solid fuel that sublimes at very low temperatures. So if you follow electropropulsion, you'll know that a big upcoming fuel that has everyone very excited is iodine. Iodine can be stored as a solid. It sublimates at very low temperatures, so it has very high storage density. It has very good performance, pretty much identical to traditional fuels like xenon, and is much, much cheaper. One of the issues with iodine, though, is it's extremely corrosive. It eats most materials, both plastics and metals, so you have to be very careful with material compatibility, and especially things that use cathodes. If you're not using like an RF cathode, it can poison conventional thermionic and standard hollow cathodes. So adamantane is actually very similar to iodine in that it stores solid, it sublimates at extremely low temperatures, and is also extremely easy to ionize. One of the things about this fuel, though, is that there's been almost no work on it in the electropropulsion field. There's maybe like 2 or 3 papers at most, and that's it. So a lot of this work that I've done myself has been pushing into very, very new territory with this type of fuel. So you can actually see here a little test cell that I actually made with just glass tubing, epoxied to a few metal plates, and there's a little heater on the bottom that sublimates the fuel. I'm applying voltage here to kind of study the discharge characteristics of this fuel. So on the left, you see kind of plasma emission in an ion mode, extracting ions. And then on the right, you actually see a mode where I'm operating it kind of as a hollow cathode would be operating. So looking at different operating modes and ionization of this type of fuel in vacuum. So here's actually a video of ionization. So this again, this type of fuel ionizes at very, very low power levels and voltages, and sublimates at very low temperatures. I've only required a couple of watts of heating power, and I've ionized the fuel at less than a watt of power. So again, very easy to ionize because it has a large molecular cross-section, being a complex hydrocarbon, and very easy to sublimate, which makes fuel delivery quite easy. Here's a video of it operating in neutralizer mode. So you can actually see a much brighter plasma plume. So this is actually wired in a way that a neutralizer would be wired. So a little bit different configuration on the electrodes to drive it. So this development was earlier on. This was back in January and a little bit of February of this year, which led to some of my more advanced developments now. So this is a hollow cathode neutralizer that I'm developing. This is the GDN1 micro glow discharge hollow cathode. And what's unusual about this hollow cathode is that it doesn't use standard electropropulsion hollow cathode technology. Normally hollow cathodes require some sort of heated insert like lanthanum hexaboride to ionize the gas thermally. There's also RF cathodes or use RF energy to ionize the fuel. But both of these require much more energy than I have available on the platforms I develop for, and are larger than I'd like. So I've taken principles from the particle accelerator field with glow discharge hollow cathode neutralizers. So where normal hollow cathodes operate at a few tens of volts, this particular cathode operates at several kilovolts, so -3 kV, to create a DC glow discharge directly. So the materials for this itself is also very simple, just a hollow stainless steel cup on the inside, laser cut stainless steel electrodes, and then literally a 3D printed housing. So this 3D printing material is Somos Perform. It's a ceramic embedded resin. This has been readily available from 3D printing companies that I've worked through to get these parts developed. So overall, this neutralizer itself was extremely low cost to make. I believe a few $100s total. And the nice thing about this neutralizer is that it's completely fuel agnostic. So it doesn't I don't have to worry about any poisoning of the cathode because it's just stainless steel. It can work with really any fuel. This was particularly developed for adamantane. So here we can actually see a video of the hollow cathode firing. So this is on the Hall thruster itself. The Hall thruster is not on, but in this test, I'm actually testing the hollow cathode itself. So this is operating at very high voltages, very low power. This is only a 2-watt neutralizer. So one of the big challenges, again, going back to electropropulsion and scaling in general, especially when you're looking at Hall thruster technology, is hollow cathodes and neutralizers in general can take up a large portion of energy. And being able to do it very low power and very small opens up now a new category of electropropulsion at this scale. Which brings me to my current development. This is a micro Hall thruster, the EHT1. So overall, extremely compact. This is about 1/3 U in total volume. Very low mass. The fuel is adamantane. So what you see here is literally everything except the control electronics. So you have the high voltage supplies, you have the thruster, you have fuel storage, you have the valve assembly, and you have the neutralizer all integrated into one super tight modular package. So the major thing that drew me to adamantane was that the solid fuel storage allows me to do unpressurized fuel storage. So it's stored as a solid inside a sublimation tank. I apply a few watts of heater power to heat it, and it sublimes the gas and delivers it directly both to the thruster head and the neutralizer simultaneously. So that relaxes a lot of criteria on the valve. So I can go with much, much lower cost and simpler valves. And the tank itself is unpressurized. So that actually opens up now Hall thruster technology to satellite classes that if you're flying as a secondary payload, it can be very challenging, if not impossible, to actually get clearance to fly with pressurized fuels. So using unpressurized fuels opens up now pocket cubes and small CubeSats for flying Hall thruster technology like this significantly easier. So the total power of this system is about 20 watts. And I am actually developing even smaller Hall thrusters now that will go down to less than 10 watts, hopefully around 5 watts. So still pushing the scaling of these technologies much, much smaller. Again, you can see I use a lot of 3D printing. So the housing itself is 3D printed. The valve housing is 3D printed. The neutralizer is 3D printed. And then relying on simplified manufacturing. So I actually went with an end Hall, which is not really seen in electric propulsion, just because it's allowed me to develop a Hall thruster without any custom ceramics. I used off-the-shelf ceramic washers and really focused the electrode designs around simplified manufacturing and assembling this. And actually, I do have a video out of this overview of the system on YouTube, which actually shows how this thing is actually assembled, at least the thruster head itself. So you can just see how simple the thruster is internally itself. So here's a video of it firing. This is actually the most recent test last month that was done. This was the most successful test to date yet. This is the first time that I achieved full ignition operating both the thruster and the neutralizer on adamantane fuel at maximum power. So this is operating at about 26 watts of power. You can actually see the plume forming out nicely. And then you have connection between the hollow cathode and the thruster itself. And those little flashes and sparkles you see are actually discharges from the Faraday Cup. My vacuum chamber is actually having a lot of time, a difficult time actually keeping up with the gas load from this. So the pressure is higher than I'd like. And because the beam current is so much higher than any of my other thrusters that I've worked on so far, it's kind of overwhelming my instrumentation and causing flashes and breakdowns in on the measurement cup. So here's another shot of the Hall thruster actually firing. So again, this is at peak power. You can see all the flashes from the collector cup due to the discharges from the beam. But you have a very stable plasma formation. Again, everything is operated at very low power. The total discharge of the Hall thruster itself is about 12 to 15 watts. The neutralizer is being operated at only 2 watts. And then the heater itself is operated, I think, maybe 5 to 10 watts itself. So even among Hall thrusters itself, this is at the very, very, very low power range. Currently on the market, the lowest power Hall thruster available is a 60-watt class Hall thruster, which even for Hall thrusters is considered extremely small. So pushing down to the 10, 20-watt class is really taking Hall thruster technology to very, very new levels. And these tests are actually the first time in the field that Hall thrusters have ever been operated on adamantane fuel. So AIS is already kind of pushing very new territory in the field with these advanced fuels and microscaled systems. So kind of to wrap things up, to show again, just some of my approach in making things simplified, firing the thrusters is good and all, but you have to be able to measure performance. So there's a few different ways that I actually do this in a more simplified manner. For like the pulse thrusters, this is an example of a simple micropendulum I built. So this is literally just from scrap materials lying around. It has a Kapton flapper head, and this is actually positioned in front of the thruster. And by knowing the mass and the displacement of the head, of the pendulum, I can actually calculate direct thrust from the thruster itself. So this is how I kind of got the impulse bit and the thrust measurements for the pulse plasma thruster systems. the cup that you've probably seen both with the Electrospray and the Hall thruster, this is a Faraday cup, so it's literally just a metal conductor that collects charge from the beam. And it's an extremely, these things can range from very, very complex to very simple. And for mine, I'm just using a copper pipe cap bolted to a peak base plate. So this thing literally cost me about $10 to make, but it's provided me incredible amounts of information, especially for ion thrusters. If you know the fuel you're using, which gives you the fuel mass, and you know the applied voltage that's used to accelerating the fuel, by observing the collected current from the beam, you can actually calculate thrust and ISP. So this is a very, very simple, low cost, but very effective way of getting pretty decent estimates on performance already from these types of thruster systems, engaging how well they operate. And then finally, this is kind of the next upgrade to this iteration. So I've taken these concepts and I've made, again, a 3D printed base with a simple aluminum extrusion and different modules that allow me to measure a whole bunch of different things. So I have, here you can actually see the Hall thruster, how it fits on in the upper left corner. And then I have a Faraday cup attachment. I have a screen attachment where I blast just a simple screen, and looking at the discoloration, I can actually look at plume divergence very, very simply and very cheaply. And then finally, I have a micro pendulum, a new micro pendulum, to allow me to do direct thrust measurements of these thrusters. So I actually can swap out thruster modules, thruster mounting, and everything very, very simply and cheaply, again, relying on 3D printing for fixturing for these types of systems. So again, you can find all of this information. I post everything pretty regularly on Twitter, Instagram, LinkedIn. There's tons of test video on YouTube, so you can actually see all the testing done to date. Everything, again, is very, very open. I walk through the theory of everything. I show all the different design steps, even all the failures. When I do testing, I do live testing now, and oftentimes you actually will see me troubleshooting the system as I go along, because a lot of times this is really the first time that I've actually operated the systems and learning. So, live chat is open, so you can ask questions during testing and really get a firsthand view behind the scenes what goes into developing these types of technologies. So with that, I want to thank you all for listening to this. And here's a lot, just a snapshot of all the different types of pulse plasma stuff that I've worked on. So again, even with something as simple as a Teflon fueled pulse plasma thruster, there's so much you can do. So with that, I'd like to kind of open up the floor to questions and address anything that you might have to ask about this particular effort.
So first off, I just want to say thank you so much for this amazing presentation. I think it was super informative, and the main thing that I've learned from this is that any field, like even if it's a very niche field and you have a lot of things to learn, if you dive deep into it, you will find it interesting. And I found this so interesting. And Mr. Micheal, I just want to say thank you. That was very well explained. So yeah. I just wanted to know one thing. So electric propulsion mostly deals with the micro size of things, right?
Like what do you mean, the micro size of things?
Like not huge rockets, like this.
Oh yeah. So, yeah. Well, it depends. I mean, a lot of electric propulsion has focused kind of on medium and large class satellites. So you're looking, a lot of the stuff that's flown is really kilowatt class stuff. There are a couple of very big thrusters on some larger NASA missions, and there hasn't been anything yet for human scale space travel, just because again, power is the biggest constraint. That's really difficult to get the power levels, because you need full nuclear generators at that point to actually do human level type electric propulsion. But on the other side, you can see that what's nice about it is that despite it kind of seeming like a more advanced type technology, because it can be operated at very low power levels, it also means that you can work on this at the small scale, and you can actually take those principles of a small 10-watt thruster and those basic principles will scale up to the higher class. So you can actually start immediately exploring this stuff at the low class and get a feel for the higher power stuff. And obviously things change. You have a lot more thermal issues at the higher power level. You have a lot of other issues, and there's different challenges at different scales. But that's kind of the one thing that I really like about it, is that it is focused on the small scale. So in some sense, it does make it a little bit more open to, you know, not everyone, you mean, even with rockets and stuff, you know, you have amateur rocketry clubs and everything, and you don't really have amateur electrical propulsion clubs, but there isn't really a reason why it couldn't be done. And I think it is kind of similar in that case, where you can still kind of explore it at that scale as well.
Yeah, that's true. And I like how you mentioned that there's different solutions to any given problem and not one approach that could solve it. Because it's very nice. And so do you have any particular project that you're, I mean, it's your business venture. So do you have any particular projects that you took up which you would say were like breakthrough defining your company? Or
since everything is still kind of very new, I have kind of looked at all different types of technologies and explored really everything to kind of best see what would fit for the applications that I'm developing for. And I've kind of really been narrowing my focus down to the micro Hall and the Electrospray stuff, because that allows me to scale from pocket cube to maybe 6U CubeSat, which covers a range of propulsion that still isn't as well covered in the field. Like for Hall thrusters, you know, the ones that are currently out there, the smallest ones, they're only compatible for 6U, but they don't go any smaller. So this kind of allows me to explore pushing things even more and creating my own kind of niche in the field. So right now I am focusing on kind of defining my efforts with the micro Hall adamantane fueled stuff, as well as the liquid electrospray as kind of my flagship type developments.
Okay, cool. So finally, I just have one small question. So there was a picture in your second slide, right, where you're like leaning next to the testing chamber. Yep. So I want to know the story behind that basement, like the room it's in. Is there any story behind that?
Well, that's my basement at home. So all the testing, everything I do is literally at home in my off hours. Applied Ion Systems isn't full time. It's all still, you know, kind of like hobby hour type stuff. So I have a full-time job at a particle accelerator where I'm an engineer at. But, you know, during the nights and weekends, I work on this own stuff. And, you know, originally when I started building my vacuum chamber, it wasn't to do electric propulsion. I was originally going to work on high power pulsed electron beams. And I had a bunch of leftover parts, and I thought, you know, electric propulsion would be pretty cool. There's a lot of stuff that I can explore and play around with, so I thought I'd give it a shot. And I started posting more about it, and it kind of caught on with CubeSat and Pocket Cube groups, and then I found there's a need and a lot of interest at this scale, so I kind of focused more heavily, and that kind of became my main focus. So the chamber and stuff that you see, you know, it's the high vacuum equipment. I've scavenged from friends who have done high vacuum physics. I've got a lot of stuff from eBay. One thing that's kind of an advantage in the US is that we have a very good surplus market. So on eBay, you can find literally everything, which has made it kind of easier for me to explore the high vacuum type infrastructure. But again, it's a much simpler, it's still a very simple test stand. You know, when you see electric propulsion companies, they usually have chambers that are big enough to walk into. And while that has a huge amount of benefits, you don't necessarily need that big of a chamber, which requires, you know, super expensive pumps, a lot of pump downtime, a lot of supporting infrastructure. So one thing that I like to demonstrate through this effort is that you don't need huge amounts of equipment. You don't need huge capital investments to actually do developments like this. So it can be done still at a very small budget.
Yeah, that makes sense. And it's nice to kind of see a hobby proliferate into a business. It's always a great thing, a great feeling actually.
Yeah, and you know, I never went into this looking to make a company. I kind of did this as a hobby to share, and it kind of just naturally evolved into that. So there hasn't really been pressure in the typical sense, because this is kind of all just evolved from something I like to do for fun.
Okay.
So actually,
that's the best, honestly.
and kind of to show kind of the scale of things, now that you can actually see my screen, just quickly, so you can actually see the scale. So some of the thruster hardware in real life. So this is the pulse plasma thruster, very, very small, compact. This is the one that's currently in orbit. This is another pulse plasma thruster. This one's kind of been retired, but you can find all the design files for this as well. So this is driving the higher repetition rate type stuff. So again, a 3D printed housing. This is with Ultem. So exploring 3D printing materials and reducing the costs. Here's the Electrospray thruster. So this is an ion thruster. So inside of here, there's actually just a porous glass disc pressed up against another disc with a spike machined into it. And then you have an extractor plate for drawing the ions out, and then a couple of switching units on the thruster itself. And then this is the actual emitter. So I don't know if you can see it, but this has a ridge machined into it. So again, this is just common chemistry filter disc. I think this disc, I got it for like 15 bucks, and I got it CNC machined. And this is wetted in vacuum with the liquid for fueling. From my first initial test with adamantane, this is the test cell. So this thing, again, this is made from scraps. It's literally epoxied together. It's really gross and cheap, but it's allowed me to explore really the fundamentals of ionization and sublimation of this fuel. So again, even working with a fuel that's almost no one has worked with in the field, there are ways of testing stuff and exploring these types of things with very simplified and low budgets. And then finally, this has been currently disassembled because I'm doing some upgrades and repairs, but here you can actually see the Hall thruster head itself. So the fuel tank and everything isn't on, but this is literally the entire Hall thruster, and then the hollow cathode neutralizer here. This is disassembled for cleaning and everything, just fits right on the side here, bolts on, and then the fuel tank assembly itself. So very, very small. So very small, very compact, very low cost types of developments. Taking Hall thruster technology, which is normally super, super expensive, and really trying to make it more affordable that anyone could work on.
Okay. So I think now we can open the floor to questions from everyone. I'd like to see what the people have to ask.
So I see, I'll read off the questions here on the side in the chat first. So from DVSS, how are thrust exactly measured? So there's a couple of ways, like I mentioned, I measure thrust. The first way is kind of indirectly using the Faraday Cup. So by taking the beam current and then reading the beam voltage and knowing the fuel mass, I can actually estimate thrust indirectly that way and calculate it out, because there's kind of simple equations for ion thrusters, in particular for calculating this. And then for more direct thrust measurements, I can actually use the micropendulum. So by looking at the displacement and knowing the mass of the pendulum, when I fired the thruster, I can actually directly measure thrust in that regard. So the next one from Shubha Murthy, recommending resources to get started with modeling and simulating electric propulsion. Actually, one of the things that I do lack myself is modeling, because modeling software is still very expensive. I do some basic modeling, so there is free software out there for doing electrostatics, magnetics and thermal stuff. And I do have there is some really great software on ion interactions with matter. So for sputtering and things, there's SRIM and TRIM, and I use some older type programs for electrostatics. But in terms of actually modeling things like plume and beam formation, that stuff is still all out of reach even for myself. I know there's a very good program that I'd still like to get. It's called Simian, which is used heavily for ion beam and electron beam optics simulations. So that's something that I would like to explore myself. But really, in terms of modeling and simulating electric propulsion, I have done almost none of that myself. A lot of it has been just really intensive research and really just kind of developing an intuition, looking at what has been done in the field, looking at all different types of things, and kind of abstracting that to my own stuff and making correlations and guesses. And then ultimately, my approach is very testing heavy. So I test very rapidly, I test a lot, and really develop my systems more through real life tests rather than modeling. The modeling definitely helps a lot because it gives you a starting foundation point, especially if you're doing a very optimized advanced system. But it's not always 100% necessary. There's a lot you can do through testing itself, and there's different trade-offs. If you have the software, then you can run essentially tests virtually to kind of establish base point, but still getting that software itself is challenging. So unfortunately, I don't have any resources on the modeling side myself yet. Hopefully, I'll be able to access that stuff myself at some point. And then Bangali Rakshita asks, how do I know the output by ANSYS is correct? Like, for example, the direction in which the grids are is right or wrong. So really, well, again, I haven't really done much in terms of modeling myself, so I'm not too familiar with that aspect. But in terms of testing, you can a lot of times the simulation is validated in the lab and experimentally. So by taking different measurements on the thruster itself, there's ways to actually characterize the shape of the plume. Having a probe scanning it through the beam and then correlating the intensity versus position, you can actually get different things, and looking at the theoretical numbers versus actual numbers of thrust and ISP, you can actually kind of validate your models. So a lot of validation is actually directly through testing itself. So Harabalaji R, how can we overcome the space charge effect between current flowing through a vacuum between a cathode and anode cannot exceed a certain maximum value? So this is actually a great question, and really space charge effects, they are limitations in not only electric propulsion, but especially in the particle physics field with accelerators and electron guns and ion guns and stuff. I mean, that defines the ultimate limits of certain types of technologies. Now, some technologies are not actually limited to the space charge effects. A lot of times you find space charge effects applies to ion electron guns, so in kind of diode type configurations. But things like plasma thrusters, for example, don't really have the space charge effect that you would typically see in these types of gun type systems. And then looking at the limits of emission, that is still kind of a fundamental limit of a material in general. So different materials and different types of emitters will have different maximums for emissions for electrons, for example. So if you have like a tungsten filament, you are at some point pretty limited on the current density you can draw from it. However, that is also kind of why things like hollow cathodes are used, because in those types of systems, you're actually drawing electrons from a plasma instead of like a metal surface or an emitter type gun like lanthanum hexaboride or something like that. So because plasma has essentially zero work function, you can get huge current densities. And even among plasma cathodes, there's lots of different technologies that can kind of get around this. So in pulse power systems, there are special types of cathodes that can generate current densities of thousands of amps per centimeter square. Plasma cathodes, you can get current densities of 10,000 amps per centimeter square. So certain technologies can actually overcome some of the fundamental limits of physical material space charge and current density effects. But at some point, you still kind of are limited depending on the technology. And I'm not sure exactly, but I don't think, like for Hall thrusters, for example, you're not really limited to the same space charge effects that you are with like gridded ion thrusters, just because there's no grid, and the principles of operation work a little bit differently. So you don't have to worry about space charge effects as much with technologies like that. So from Srikar Gadavimula, and I apologize if I'm not doing your names right. In ion propulsion, the charged particles are accelerated at high speeds. Are the energies of those particles just enough to produce ionizing radiation, or energy supplied in your case? So yeah, actually, that's a good concern, because in vacuum, when you have a beam of some energy and you're hitting materials, at some point you're going to be liberating X-rays. At electric propulsion levels, this isn't really an issue, because typically in vacuum you need accelerating potentials of around 20,000 volts for X-rays to actually start coming through, the chamber walls and viewports and stuff. So, at 1,000, 3,000, 5,000 volts, the X-rays, if there are any that are detectable, they're very, very negligible. So you don't actually have to worry about this for electric propulsion. Now, if you're looking at super high power systems, at megawatt class for, theoretical for human level space flight, then you might actually have to start worrying about significantly more shielding at higher power levels and depending on the voltages used. But at least for standard electric propulsion, ionizing radiation really isn't an issue for these types of systems. So that's it for the written questions that I see. I don't know if anyone else has any more questions they'd like to ask or anything, but.
Hey, so I am Shankar. So I have one question. So in the future, how do you think do electric planes be able to reach supersonic speed? Will it be able to reach supersonic speed in the future by using electric propulsion?
I'm sorry, could you repeat that?
In the future, could electric planes reach supersonic speed?
So yeah, there is a lot of interest in applying the electric principles to those types of aircraft and structures, and there's actually a lot of interesting things in terms of what you can do with especially the plasmas. So for supersonic and hypersonic systems, you have plasma systems for enhanced ignition, enhanced combustion. There are things being explored for like plasma actuators on wings and stuff to allow for better aerodynamic control and everything. But it is still kind of a challenge, because all these systems require a lot of power. So whatever gains you get, there are still you have to balance the trade-offs with the power required. And in terms of standard, if you're looking at airtight propulsion, like propulsion more in air instead of in vacuum, there are significant challenges in applying these techniques to conventional propulsion, just because the physics doesn't really allow you to, electric propulsion doesn't give you very much thrust, as opposed to chemical type stuff. Now you can't, like I said, you can't take the principles of the plasma physics and ionization systems for fuel optimization and enhanced combustion, more stable combustion, to help out with the chemical kind of side. So you can actually complement each other in that aspect. But in terms of certain aircraft using this type of stuff, it's much more challenging, and really you can only see the benefits in space. There is a lot of work for stuff with very low Earth orbit, so actually combining ram air intake with some sort of RF thruster or some sort of modified Hall thruster to produce thrust at lower orbits, where it's not like space where you have a lot of atmosphere enough to actually collect fuel. But again, those types of things still require the cost is still power, which applies fundamentally to any type of electrical system, because ultimately you're using electrical power to ionize the fuel. So there are definitely challenges associated with that aspect still.
Thank you, sir.
Okay, so Nikison M asked, UAV being currently developed domain, are you currently working on UAV propulsion? So at this point, I've been really just focusing primarily on nanosat and picosat stuff, just because, again, there's so much to be explored in this area, and especially kind of bringing the cost down, I think is a big challenge that'll help open up this type of technology to a lot more teams out there. So I haven't been doing anything with UAV type development.
Hello. Hello, sir. I have a thing to ask. What are all the kinds of electric propulsions that don't qualify as ion propulsions during the standard space flight?
Yeah, so really, it's always a little bit kind of difficult, because there's some things that kind of have crossover, and kind of gray area. Like you have your ion thrusters, and then kind of separate to that you have the plasma thrusters. So really, the way some people like to distinguish the difference, some people don't. For myself, I like to distinguish ion thrusters as specifically accelerating ions out and neutralizing the beam. Whereas plasma is you're accelerating out kind of a bulk, quasi-neutral type ionized gas mix of ions and electrons as a plasma plume. So in the way that I classify things, like the plasma thrusters aren't classified really as electric or ion thrusters. And then you also have some interesting technologies like solar sails, for example, is a type of electric propulsion-ish type thing in its own category. You have tethers, which they're not ion thrusters themselves, but they can use principles like active tethers use electron guns to emit charge, and it creates a charge differential across the line, and you can actually raise or lower orbit based on the magnetic fields of Earth interacting with that line. So there are still kind of some other propulsion technologies that aren't classified in that particular area that still share similar principles in terms of some of the technologies used, like a neutralizer for a Hall thruster, for example, which a Hall thruster could be considered an ion thruster. That neutralizer could also be applied to active tethers, but the tether itself really isn't considered an ion thruster, because you're not expelling ions to cause that type of acceleration.
Got it. Thank you.
So Kailash R is asking, what is your plan for outreach for the technology that you're developing? Who has approached you showcasing their interest? So really, in terms of outreach, everything that I've done so far has been heavily social media. So really, a large part of, I think, which has made this effort more visible is just openly sharing everything on social media. So sharing things on Twitter and Instagram and actively engaging people. One thing that's kind of unique about Applied Ion Systems in the field is, because it's not very secretive, I'm always open to just discussing things with anyone across the field. It doesn't matter if you're a high school student. It doesn't matter if you're a seasoned veteran. I've been approached by everyone across the board. I'm always happy to discuss and talk about this stuff, because ultimately, at the end of the day, at least for me, I don't think it's really I mean, hoarding knowledge and hiding it away, I mean, at the end of the day, maybe it benefits myself, but it doesn't really help anyone else out. And I don't have the answers for everything myself. So putting that stuff out there, maybe someone else can solve a problem that I can't. And in terms of approaching me, interested in it, I've definitely been approached by a bunch of teams in the nanosat and picosat communities, and this all again has to go back with just sharing it on social media, talking with people in the field, and really engaging people at a personal level. A lot of these groups, they're small startups themselves, working, a few people developing CubeSats or pocket cubes, and on often lower budgets and things like that. And the community is very small, so there's a bunch of different chat channels. There's a couple of Discord channels that I've actively talked with. There's a Facebook chat group and stuff for pocket cube developers and stuff. So really engaging with people directly instead of being secretive and trying to hide away the specs, I think has allowed me to be approached. And actually, that was the reason why I first sent my first pulse plasma thrusters out to the MSAT Spain group. And I was sharing with the Pocket Cube community, and they approached me and they're like, hey, we have some payload space and we'd be interested in trying to fly this stuff. And I think that's kind of how a lot of it comes about, is because I'm developing these things specifically at a cost and power level that can be accessed by these types of groups. So the next question, can we use multimode propulsion for satellites to perform orbit maneuvers? So actually there has been a lot of interest in multimode propulsion, and I've talked to a bunch of people about this type of stuff before. And really, when you're talking about multimode propulsion, there's a couple of different ways you can define it. You can have a single propulsion system that operates in two different modes. So a high thrust, low ISP mode, and then a low thrust, high ISP mode. So one thing that you actually see being developed actively in this area is electrospray, particularly for ionic liquid electrospray. If you can control the flow rate of the fuel actively to the emitters, you can actually readily change between a low ISP, high thrust colloidal mode, where you're just spraying out droplets, and then pulling back the flow rates, so that way it's so low that you're not spraying droplets, but you actually start emitting ions from the emitter. You get high ISP, low thrust modes. So in that ways, that's actually very much being actively explored for orbital maneuvers, especially at the nanosat level. Then on the other side of multimode propulsion, you have kind of complementary setups. So you have two separate thrusters that are being operated off like the same fuel. So you could have there have been some thrusters or systems where you have chemical and electric propulsion kind of working together, as and the operation kind of integrated together to complement each other. And then you also have some electric propulsion that people have explored, burning the fuel as combustion and then accelerating the fuel separately as ions, depending on how it's operated. So there's a whole bunch of different ways of exploring it, and all this stuff is really ideally for different types of orbital maneuvers. So for the high thrust mode type stuff, it allows you to do bigger jumps, it allows you to do more rapid changes. And then for the low thrust stuff, you can do more fine precision flying, collision avoidance, or not collision avoidance, but flock formation and type of stuff like that. One thing about the multimode that you have to remember, especially if you're doing a single thruster that operates in combustion or ionization mode, is that you lose a lot of benefits of both types of technologies. And I think this is where, because I've seen electrospray stuff, for example, where people have tried doing multi-mode, where you actually burn the fuel and then ionize the fuel as electrospray, and you can't. It's hard to optimize the optics for electrostatic acceleration simultaneously as like a thermal nozzle for combustion. So you end up losing a lot of benefits that you might gain theoretically. So I don't actually really like the multimode from that perspective. Where I really see multimode as being powerful is combining multiple systems together as one larger unit. So this is kind of where you could see benefits of having, chemical and electrical propulsion separately, but working together to complement each other and offset each other, or the types of stuff like the Electrospray, where you can change between modes, not through either combustion or ionization, but changing the ionization where you have, either droplet spray or ion spray in that regard. So the next question, electric propulsion is known for quite a long time, proven effectively, then why has it not been used extensively? That's a good question. I think a lot of that, again, comes down to cost and technological constraints, in that traditionally electric propulsion systems are very, very complex. Gridded ion thrust, there's three major technologies that you see commonly, especially at the higher power level for larger satellites, which larger satellites currently are what use electric propulsion more. You have, the Hall thrusters, which are by far the most ubiquitous type of thrusters out there that most satellites use if they have electric propulsion. You have gridded ion thrusters, which are used really catered towards deeper space type stuff. So NASA missions and stuff where you need very high specific impulse, very high fuel efficiency. And then kind of RF plasma thrusters, where you're kind of seeing more of this emerging for low Earth applications, because it has lower ISP, but good fuel agnosticism, so you can use any fuel, so it makes it kind of easier in that aspect. But still, the big constraints are cost. And the way that these things are developed, they're again not really developed from the standpoint of everyone using them. Usually, traditionally, electric propulsion is developed from the standpoint of, big NASA budgets, big military budgets, huge commercial budgets. So they haven't really been developed in a way that anyone can just access them as much off the shelf. Now, that a lot of that has changed with kind of the CubeSat revolution in the past couple of decades. And then the emergence now of pocket cubes and stuff, because so many more people are getting into smaller satellites, more lower cost satellites, that it's driving a need for more affordable and accessible propulsion. Because prior to the CubeSats, you really just had big satellites that had big power budgets and required, big complex systems. So I think that, now, while the electric propulsion has been known for many, many decades, because the satellites that have been developed haven't been at the scale where they're more accessible to everyone only recently. I think that's why we haven't really seen them as much. But certainly, with all these new companies emerging, we're seeing a lot more of this. I mean, in the CubeSat space, there's almost a new company coming out, every other week or every month or so. So there's tons of companies emerging in this sector, really pushing new innovations in electric propulsion. So they are still costly. They are coming down in cost, but they're still kind of costly. So I think once there's more demand and more people launching CubeSats and smaller satellites, we'll see a lot more of that stuff being flown. So from that standpoint, technologically, it's not the issue. I think it's, again, more the issue of the platforms that they're riding on just haven't been to the scale where it's more accessible. So the next question, is it possible to combine any green monopropellant and ionic liquid for multimode propulsion systems? So yeah, there have been there has been some, well, it's difficult because for ionic liquid, you need a liquid that is vacuum stable, so something that doesn't just evaporate away in vacuums. So it has to have negligible vapor pressure, and it also has to be chemically in a way that you can actually extract ions from. So you can actually use, for example, monopropellant, like if it's a liquid, in liquid form, you could potentially use it in something like a colloidal electrospray, which is an ion spray. You're accelerating charged droplets of liquid, and kind of the older fuels used decades ago for that particular stuff was certain salts dissolved in certain liquids like formaldehyde or something like that. And on the multimode side for ionic liquid, there are a couple of ionic liquids that can also be combusted as well. So that's what have kind of drawn people to that multimode type thing. But again, there are challenges sharing both types, combustion and ionization modes, with the same exact thruster output, because if you have a nozzle, you want it shaped properly for optimal thrust for the combustion mode, and it has to be thick enough to stand the thermal stresses of that. But at the same time, if you have the output nozzle that's too thick, that's going to severely impact the ionization or the actual fields for ion mode, because then it won't be optimized for the ion optics. So there's a lot of trade-offs that I think, in some sense, it's ultimately better to have two separate systems kind of working together. But green monopropellants could maybe be used for electrospray. I wouldn't say necessarily ionic liquid electrospray type stuff, but it could possibly be used in colloidal type systems. So the next question is, can you go into details about how Rocket Lab's Rutherford engine works? Unfortunately, while I'm very, very knowledgeable about electric propulsion systems, I actually don't have any idea how the chemical side of stuff works. I'm not very familiar with the rocket engines. So unfortunately, I can't go into how those types of stuff worked. I've just spent so much time focusing on electric propulsion that chemical propulsion side is a little bit of a mystery to me. So I guess this one final question: can we use magnetic shielding to achieve efficient energy transfer and higher transmission power? So there has been a lot of work done, especially in Hall thrusters, for magnetic shielding, for increasing the performance of Hall thrusters, not only from the erosion standpoint of where you're minimizing erosion, but also shaping the fields in a way that it's more optimal for the acceleration mechanisms and ionization mechanisms, especially at the smaller scale. Magnetic shielding does actually come a lot into play for helping improve a lot of inefficiencies you kind of see at the very low power scale. So there is definitely a lot of interest in magnetic shielding to increase efficiency for in particular for Hall thruster type stuff.
Okay, I think with that, we're about ready to conclude our session. So before we let you go, Mr. Micheal, I just want to know, where do you envision your company, say in the near future, and what are your goals mainly?
That's a great question, and I think ultimately, I'd like to grow this effort larger, and really the ultimate goal is flying the thrusters, getting as many thrusters out there and then flying more of them. And really, I'd like to see Applied Ion Systems kind of be not only this unique entity in the field that approaches it very differently from convention, but kind of being a leader in electric propulsion at the very small scale, and kind of covering the area of propulsion that traditional companies don't usually do. So almost entry-level propulsion systems, lower cost propulsion systems, and ultimately, flying as many of them as possible. I think it'd be cool to have Applied Ion System as kind of one of the kind of default companies, if you will, kind of for propulsion at this scale. There's definitely a lot of competition, especially in the space where everyone is super heavily funded. So I have to push myself extra hard to kind of keep up with those developments and really take on some very unconventional stuff like the adamantane fuel, trying to take advantage of things that people haven't really explored before to give me a unique edge. But ultimately, hopefully, you know, I hope this grows into something bigger. I can't say where it'll lead to eventually, but I'm hopeful that someday it'll be a little bit more than a typical basement effort and be something that I could, you know, actually make a solid living off of itself and expand more and be more recognized in the field.
Okay, that's really fascinating. And honestly, it's a great vision to have. And the fact that you're so open to collaboration makes it even better. So yeah, I think it's very relatable for a lot of people who are like interested in stuff like this and want to start working on it by themselves, that they shouldn't just give up because they're like, say, have a lack of resources or something. They should just, you know, try to work on their interest and develop it further. So yeah, huge respect to you for trying to make it more accessible. And I am really like excited to see where it goes. So thank you so much for your time, Mr. Micheal. This was an amazing session. I learned so much, and I'm sure all of us did. So on behalf of the club, as well as everyone who attended, I just want to say thank you for your time. And it was a great motivation for a lot of us who have really big dreams and want to start working on them.
Yeah, and thank you very much for the time to speak. Like I said, I always enjoy, you know, talking with anyone interested in propulsion stuff. So it's always great to be able to share these experiences and hopefully inspire others interested in the field to keep pushing, regardless of your resources or background or anything, because I think there's a lot of room to be able to innovate if you take unconventional approaches that people kind of ignore.
Yeah. So I hope to do more sessions with you, and all of us do, as I'm speaking on behalf of the club. So we're really looking forward to it, and thank you so much.
Thank you.
Okay, bye-bye.
Thank you, sir.
Thank you.